odd, Steven. Numbers, huh? I know how to count. 1, 2, 3, 4, 5, 6. Let's move on. So I was reminded by how high can you count on your fingers? And it's an awesome video and you should take a look at it. But I think I can do better. I'm pretty smart. I can count to at least 6. So let's just throw in a little refresher about the TED Ed video, and then we'll move on from there. You can count to 10, that's pretty easy, but you can count up to 12 on a single hand by counting every section on your finger using your thumbs. You can count to 24 with that, 12 on each hand, but you can do a lot better with a tiny change. Every time you reach 12 on one hand, you increment the other by 1. Doing this, we're counting 12 times 12, 12 squared, or 144. That's a huge improvement. We can bump that 12 up to 24 by not only counting the sections, but also the ridges between the sections. So we end up with 6 ways to count on a single finger. 24 times 24 equals 576. Then we get into the really cool ones. By treating our hands as binary and doing the same multiplying deal, we can represent 1023, an even bigger jump. We can represent this as 2 to the 0 plus 2 to the 1 plus 2 to the 2 and all the way up and 2 to the 9. Or we can do 2 to the 10 minus 1. If we're working with binary, notice that every finger held up means that you're 1 away from introducing that 2 to the 10. So we just minus 1 from that. Here's where the video ends technically, because you can go higher. If you hold your fingers halfway up, you can get a third state, 3 to the 10 minus 1, which is 59,049. But the issue with that, and counting 24 on one hand, is that it can get tough to count. Sure, you can do that, but when you're trying to count numbers, you're not focusing on your hands. So when you look down, this might be a 1, but it could also be a 2. No, we need some distinct way to show numbers. Here's what I found. Going 12 times 12 does work, but we're missing something there. Let's try on a smaller example first. Let's say 5. So we can count up 5 on one hand and then transfer it, keep going, and we get 25. 5 times 5. But we still have an extra hand to count. An extra 5 in this case. So it's not just n squared, but n squared plus n. So if we use our 12 case, that puts 12 at 12 squared plus 12, 156. We can come up with a nifty little equation to represent this. If we treat this as an ordered pair, think xy coordinates, L comma R, we can represent what number each hand represents. In our 5 example, we can have at most 5 comma 5. And with 12, we have 12 comma 12. So how do we find out what number we're representing from that? Imagine working with 5, and we have 3 comma 2. We know that every number on our left hand represents 5. So 5 times 3 equals 15, and each number on our right represents 1. 2 times 1 equals 2, and we add 15 and 2 to get 17. So for any n ways to represent a number, a comma b represents the number n times a plus b. Looking back at our binary situation, one hand is able to reach 31 numbers. When we use our equation, 31 squared plus 31 is equal to 992, which isn't quite our 1023. And side note, 1023 is the highest number we can count, but we're including 0 there, so we're actually able to count 1024 numbers. But we'll stick with 1023 for now. Let's go back to our squaring idea though, because we're missing something here. We're losing valuable real estate because we're not actually doing math here, at least not correctly. Theoretically, we'd like to not waste a single hand position. Any number should only map to one hand position and vice versa. This is called an injective property, and we've secretly been doing this wrong the whole time. Let's take a look at a smaller example again. Our trusty 5. It's almost as if counting 5s and 10s are the easiest ways to count. Who'd have guessed? So we can count to 5, then we increment the other hand up by 1. This way we can count up to 30 on both hands. But did you see the issue there? It's not actually injective. We're treating 0, 5 the same as 1, 0. and we're losing valuable numbers doing that. But let's say we count up to 0, 5, and then we add 1 to get to 1, 0. Then how far do we get now? Well, we see that if we're using 5 fingers, we'll be able to count up to 35. So let's fill out a table for the other smaller numbers. We see 4 goes to 24, 3 goes to 15, 2 goes to 8, and 1 goes to 3. And we might as well throw in 0 there for fun. 0 goes to 0. So there's a pattern here, and it seems to be n plus 2 times n. But where exactly is this coming from? It feels a bit arbitrary, doesn't it? How do we get that number? Let's look at 1. We see that 0, 1 equals 1, and then 1, 0 represents 2. Let's take a look at 2. 0, 2 equals 2, 1, 0 equals 3, 1, 2 equals 5, and 2, 0 equals 6. Let's fill out the table, and we see a relationship here. Every time we have 0 on the right-hand side, our total number is a multiple of n plus 1. We're onto something here. To represent the left-hand side, we take n plus 1, and we multiply it by the number of fingers we have, n. So n times n plus 1. We have that empty right hand, which is just n, so n times n plus 1 plus n, and that's n squared plus 2n, which we can simplify into n times n plus 2. And we got it. This should be an injective form of counting where we maximize our numbers. N times n plus 2 is our new equation. So, for any ways to hold up a unique finger pose, the ordered pair AB represents the number A times n plus 1 plus B. Taking our 31, we plug that in, and 1023. We reinvented binary. Probably should have seen that coming. We really are just exhausting every possibility and then incrementing by 1. And that's exactly what binary does. Whatever, let's move on. At least we've proven them to be the same, and we can sort of double check our work using both methods. So how can we improve on our 1023 then? We want some discrete movement that can't be easily confused for another movement. Palms work great. We can either hold a palm up or down. With 2 palms, we should get 4 times the count. Let's double check that by using both methods. Let's start with our binary case. 1023 possible numbers and 4 different states of our palms. 1023 times 4 equals 4092. We can also think of this as just extra binary cases. Since each palm is either up or down, 0 or 1, we can just use our binary formula with 2 extra digits. We originally had 2 to the 10 minus 1, so now we have 2 to the 12 minus 1, which equals 4095. That's not the same number. That's weird. Let's go back to that. But first, we'll try out the second method. So we have 31 ways to represent one hand, so that one hand has that one palm. So we get to double the options. 31 times 2, 62. So our n should be 62. Plug that into our equation, and we get 3,968. What's going on here? Ladies and gentlemen, I present the cause of most problems in computer science, the humble 0. Remember how I said we actually had 1,024 numbers, and that's because we need to represent 0? So when we're multiplying 1023 by 4, we're actually saying that we have 4 different ways to show 0. So we have 3 waste positions. That sure seems like 4,095 is the right answer. So let's try to figure out where we went wrong with 3,968. 31 isn't the number we can count. It's 32. 32 times 2 equals 64. Using 64 as our n, and we get 4,224. So now we're a little too high. It looks like we need to multiply 32 by 2 and then subtract 1 to remove our 0. With the binary, we want to keep that in, but because we're filling up the right hand to increment the left, we actually want the max number we can reach. So instead, we'll try n equals 63, and we get 4,095. And there you have it. 4,095 is probably the highest you can reasonably count. In the end, binary probably is the most efficient method. I'm sure you could get higher, but certainly at the cost of efficiency and readability. If you have any ideas on how to count higher than that, I'd love to know. I'd say the only requirement is that it has to be using only information from your hands, and any kind of intermediary movement, like a finger half bent between the states of fully up and fully down, are invalid. I was really hoping that the squaring method could surpass the binary method, and the number of times I made a mistake because of miscounting by one made this way more confusing than it needed to be. If you try this, you should totally let me know how you fare, because I'm sure there are a lot more optimizations left. Could we count maybe just 1,000 more numbers? What about reaching magnitudes higher? If we're able to reach some insane number, I might do a video counting them all. Unless it's more than 10,000 or something. That's way too much. So I guess you can count to 4,095. Beat that, Ted. P.S. Please let me on TED Ed. Please, 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 please. I've got a mean talk on how there are too many Spider-Man. Please, 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 please.